Okay, so today we had the pleasure to have Will Gus here speaking to us about his work toward neural homology theory. Will is a PhD candidate in the machine learning department at CMU and co-founder of InfoPlay AI. He is advised by Dr. Ruslan Salakutinov, and his research spans reinforcement learning, natural language processing, and deep learning theory, particularly at the intersection of algebraic topology, computational geometry, and learning theory. William completed his bachelor's in pure mathematics at UC Berkeley, where he was awarded the Regents and Chancellor's Scholarship. During his time at Berkeley, William received Amazon Alexa Prize grant for the development of conversational AI and co-founded ML at Berkeley. So, Will, take it away.
Cool. Yeah, so today I'm going to talk to you about a little bit of work on algebraic topology in relationship to neural network theory. And the way I want to motivate this is with the problem of architecture selection. So, in the past couple of years, deep learning has been really successful, mainly in large part because we've eliminated feature engineering, right? We're not using hog filters anymore. And as a result, research focus has really shifted to instead of finding the best features, finding the best architectures, Like, given two architectures, how do you compare them? Which is going to perform better in your test set? And a large part of this is really focusing on how you build inductive bias into architectures. So choice of convolutional architectures versus fully connected architectures, residual connections, et cetera. This is really important. And then in computer vision, for example, a large body of work, focuses on improving these initial architectural choices of, AlexNet even. And if you start looking at what architectures look like in different domains, like natural language processing, you start getting these very hyper-specialized architectures. And these are extremely successful, but it sort of leaves a question: what is it about the data that leads to these architectures? So there's this issue that if we keep approaching it this way by imparting inductive bias on these data sets, it doesn't allow deep learning to scale without expert-level architecture designers. So if you want to implement automatic deep learning, et cetera, using this approach, it's been very successful, doesn't really scale. And there's several solutions to this, right? So there's this whole work on neural architecture selection, there's Bayesian hyperparameter optimization, and it works really well. Recently it's been sped up extremely well, but the main thing is it doesn't capture what it seems that this year at NIPS seems to be the best tool in the deep learning practitioner's toolbox, which is inductive bias. These methods are sort of blind to the data, and it's not really clear what features of the data should influence architecture selection, right? Sort of if you look at neural architecture selection in general, like the algorithms by Zolf and Kwok Lee, you kind of see that they're using this reward signal, which is how well did the neural network do on the data set, as this sort of implicit representation of what the data looks like. But we think we can do better than this, and not just improving architecture selection, but sort of understanding what is it about the data that makes architecture so successful. So there's a partial solution here, and it's to use neural expressivity theory. So just in general as a primer, basically neural expressivity theory tries to relate the properties of neural networks, like how many layers, the width of a neural network, to basically the capacity of that neural network to generalize and express certain functions. You'll get results like shallow networks need exponentially many more units than these deep neural networks to express certain polynomial functions, et cetera. But there's a caveat here that you need to know, if you're trying to use architecture selection, that you need to know what polynomial function your data expresses. You need to know the curvature of your data. All these things are super important, but you can't get it efficiently without sort of solving the problem in the first place. And so we're going to propose a sort of different lens, something that's more computational here. So given the statement of architecture selection is, you have this sort of data set or learning problem, and you're trying to ask which architectures are suitably regularized enough and expressive enough to learn and generalize on that problem. So data-first architecture selection says, well, if you can come up with some sort of computable measure of data complexity, and then characterize neural networks by their ability to learn subject to that complexity, then you can sort of seed architecture selection. So one particular example of this is take these two data sets here, right? So we've got D1 on the left and D2 on the right. D1 is just, two classes. I've omitted the second class, but it's the complement of the first. And it's got, two balls, two separated connected components with a uniform sampling on those balls. And the second data set's got two balls and two rings, same sort of setup. Now, if you train a 12 hidden unit, single hidden layer neural network on this data set and a 26 hidden unit one, they both learn. They both at least capture these connected components. But if you try in D2, no matter what initialization of this 12 hidden unit neural network you give, it'll never express these rings perfectly. There will always be these adversarial sets right in the middle. And this is saying something that if you capture that D2 is somehow more complex than D1 and sort of characterize the architectures by this complexity, then if you could compute this complexity, choosing an architecture or a set of candidate architectures, so for neural architecture search or Bayesian hyperparameter optimization, would be as simple as computing this sort of prior, this notion of complexity of the data and imputing it on the algorithm. So to give you a more visual representation of what's going on here, you have a 2-unit neural network, a 4-unit, 8-unit, and 16-unit, same data set. And if you sort of look at the best case, if you sample 100,000 of these neural networks and look at the best sort of convergence, you can see the 2-unit neural network, as you expect, will only capture this sort of one component. These red things are just a bunch of data points. So there's so many data points here that it looks like it's solid. But if you zoom in close enough, it's just data points. And the complement, this is one class, and the other class is sort of omitted here, but it's everything else. So it's whatever's inside of that red ring right there and outside of that red ring, et cetera. And if you sort of look at this, no matter how you initialize this 4-hidden unit neural network, it's never going to capture that sort of ring there. But if you go down to the 16-hidden unit neural network, it captures it. And in the 8 one, it doesn't actually capture the ring. So there's adversarial examples here. And this happens in different orientations, but this is sort of a phenomenon we observed. 6 units, sorry. Yeah, so I'm just giving you an example with 1-layer neural networks. But the work here we're going to do is we're going to develop this sort of notion of data-first architecture selection for multiple-layer, multi-connected, or fully connected neural networks. So that's sort of the picture you should have in your head here. But how do we develop this notion of geometric complexity in the data? And so what we're going to use here is this tool called topology. So the main tool of topology is just sort of these continuous maps. And the classic example I can give is sort of what defines equivalency in topology. So in topology, you have 2 sort of sets, geometric shapes, for example, and you kind of say these 2 shapes are equivalent if you can sort of continuously deform one shape into another. So the classic example here is the donut and the coffee mug, and there's a sort of deformation. I'm being a little loose here with what it means to be equivalent in topology, but this captures sort of the same notion. So there's certain invariants that are captured, like the number of holes, the number of connected components, etc. And it can differentiate sets, and sort of we're going to get to data sets here in a moment. It can differentiate them in a meaningful way that discards certain information that might be even harder to compute. So what does it mean to have what is the rotation of MNIST, for example? What is the translation of MNIST relative to the origin? All these things that are other interesting geometric properties, topology discards. But we find if we use this geometric notion of complexity, that it actually kind of characterizes and delineates neural networks in a very, very powerful way. So just going back to the original example, D1 is not equal in topology to D2 because you've got 2 clusters here and 4 clusters here. And at some point, you'd have to split. You'd have to make a tear in this cluster to produce at least one of these other 4 clusters here. So in a sense, these data sets are unequal. And the next thing is, so OK, we've got a notion of how to separate data sets topologically, roughly. Yeah.
Have to do with like solid objects and things
so we'll get there. So just I'm assuming that we're talking about the distributions here. Like if we looked at the support of the distribution up to a certain level set, then you could say that these data sets are different. But we'll get to, I mean, you've heard of persistent homology, I think, from a previous talk, but we'll get in how this is sort of plays in here. But roughly speaking, these data sets, the true distributions of these data sets are different. So the next tool we're going to use is some way to actually kind of compare the complexity of a data set. So there's this tool called Algebraic Topology, which roughly takes these sort of spaces, these topological spaces, and converts them to algebraic groups, rings, other sort of algebraic structures which are discrete. And these structures we're going to be able to use are, we'll boil them down to a set of integers which we compare, which will show that certain data sets are more complex than one another. So just to give you some background here, I'm going to be very rough from a topological perspective, but we're going to define something called homology. And it's roughly going to count the number of holes. The notation we'll use is z to the 1, 2, 3, 4, 5, whatever it is, where the power of the integers here is the number of holes in dimension n. So to give you just a rough example of this, if we look at D1, the number of 0-dimensional holes, this is a caveat, it means the number of connected components. Number of 1-dimensional holes is like the number of sort of rings, and the number of 2-dimensional holes is the number of cavities. If we look at D1 here, we've got 2 different connected components, and homology would give you that. It would give you that you have 0 1-dimensional holes and 0 2-dimensional holes. If you go look at the second data set here, homology is going to give you that you have 4 separated clusters. And then in 2 of these clusters, you have holes, right? So it'll be two one-dimensional holes. And right off the bat, if we were going to apply some reasonable partial ordering to sort of this homology right here, we could kind of say that D1 is sort of less complex than D2. And this is what we kind of saw. So first of all, D1 is less complex than D2 in topology. And in terms of neural networks that can train and actually express the decision boundary properly on these data sets, the simpler data set is easier for 12 hidden units and impossible for 12 units on the second data set. So this is basically the basis of our talk. We're going to use this tool called Homology here, and we're going to characterize the capacity of neural networks. And just as a brief aside, this Homology tool, it doesn't capture everything about topology. But if the spaces are equivalent, then you get this equivalency in the homology here. Basically, the powers are the same if the spaces can be smoothly transformed into one another. Anybody have any questions at this point? Just a basic primer. Yeah.
I guess a high-level question is: it seems like the difficulty in homological space may not correspond to the difficulty in neural network learning space. So
right.
It could form a two-connected component space that would
with
be
a bunch
hard.
Yeah, with a bunch
for
of
neural
squiggles.
network to learn.
Right. So here's the caveat here. I mean, data first architecture selection says take some description of your data and help that guide neural architecture search, right? So you don't necessarily use all of your inductive bias on the data to decide an architecture. And the same thing holds here, right? We could easily come up with another measure that would be the curvature of your data set and say, let's characterize, if I have a data set that has a variation on its curvature, if I kind of walk around the data set and sort of there's a lot of spikes and there's not a lot of regularity to the data set, do I need 50 hidden units or 500 hidden units or 30 layers? You could do the same thing here, and I think that would be a great piece of follow-up work. But we're just starting with topology because it's sort of something that you can approach in terms of computation, and you can also sort of visualize very easily. So, yeah.
So I have a doubt about starting with a topological space. I'm thinking about situations where I have to do some text processing, and I'm thinking, do I want to treat words as the atomic units, or do I want to do a character level RNN sort of thing, or try to do morphological or something?
Right.
And to me, it feels like these are not even the same topological spaces, and so I don't even know whether I understand.
So like comparing like a character level representation of sort of NLP data versus like right. Well, I mean, one thing you could argue here is that if you do have a continuous mapping from one to the other, somehow if you start with one topological space, it's sort of depending on what that mapping looks like, right? Is some of the topological information is being preserved. So like one thing with continuous mappings is if you have a space with a certain number of connected components and you push it through to another continuous mapping, you basically do an embedding or some sort of projection on, let's say, the word level representation. The number of connected components is preserved. So that might be one way to look at this, I think, is that, sure, these different representations might have different topologies, but if you're kind of continuously going in between them, then this notion is still a little bit nice. But what is entirely unclear to me is how, for example, in language data, like what does the space even look like there, right? Is it a trajectory through? I mean, you could imagine it just being a trajectory, and then you're sort of looking at the topology of all the trajectories. You could sort of come up with a higher level embedding and look at that topology. It's unclear there, and I think there's a lot of work that needs to be done to sort of flash that out. But at least starting out with this nice real value data is our first little test case here. There's something interesting going on, and you'll see in the empirical study we'll give in a moment that there's actually like a clear delineation. I mean, sure, curvature could play a role, but if you have these data sets of varying increasing topologies, there are neural networks which can and cannot express these topologies.
And this approach is very good for image, this kind of continuous data set, but for language, the data structure, I guess, is more like the tree structure than topology. In fact, if you only counts about these holes or connected pieces, then you have difficulty to deal with trees.
Right. Yeah. I mean, I don't know. I don't have the solution here. It's entirely unclear how you approach this in an NLP setting. But I do have some sort of faith because you kind of get these nice continuous word embeddings. Although it's discrete, you do get continuous word embeddings. So I kind of have some faith that, maybe it's not captured by this continuous notion of topology, but there could be approximations. I mean, that's an open question. You should write a paper on it. But there is some work actually on capturing the persistent homology of NLP data. So this came out of CMU, I think, about a year and a half ago, and I'm happy to talk offline about this. So, yeah.
Simple topology question. So, is hx equal to hy implies x
No. So think about it this way, right? You have a topological space, and homology is a sort of flashlight you cast on this space, and you see a certain shadow. But you could take the flashlight and move it to a different angle and capture a different shadow. So just because the shadows are the same doesn't mean the spaces are the same. If that makes any sense. It's kind of like a coarse lens with which we look at topology. Okay, so we've got this notion of dataset complexity. And now we want to sort of ask, okay, well, what sort of neural networks can express certain topologies in their decision boundaries? Just looking at the neural networks now, not the data sets. So first thing is that should be apparent is that homology is actually sort of a stringent measure for characterizing neural architectures, or topology in general. So if you've got some sort of topological manifold, so let's say this is where your data distribution lives, and we denote the sort of, for any function, we denote the homology of the support, so the number of holes in the support of that function by this h sub s thing, then there's sort of this really natural notion that if none of the functions in your function class express in their support the topology of your space, right? They can't express the same number of holes. There's always going to be some sort of adversarial set. And this is kind of a trivializing result, but it kind of tells you that this provides a minimality condition. So if there's like 10 holes in my data set, my function class can never express 10 holes, then there will be an adversarial set. So this is just...
By support, you mean f of x greater than 0 or not equal to 0?
F of x greater than 0. Just think about positive valued f right now. I'm just...
a soup level set.
Yeah.
The support usually is meant.
Well, yeah, it should be anything that's unequal to. Yeah, exactly. That's why I've not actually. Well, I've written support here, but.
That's fine.
Yeah.
Just clarifying.
Yeah. But so this is sort of the condition we'll use to say that if I have a bunch of neural networks and none of them express the topology, then if I have a data set that truly has more holes than this neural network class can express or this architecture can express, regardless of initialization, then there will be adversarial sets. Okay, so if we kind of frame everything in the lens of topology, we can sort of look at architecture selection in the following lens, right? Given some sort of data set, which architectures express function classes which then have support homologies or positive support homologies that are equivalent to that data set? In other words, which architectures can express the same number of holes as in our data set? This is the question we're going out to answer. So we'll first do an empirical characterization here, right? So the first thing we'll do is we'll generate data of increasing homological complexity. We'll apply random different perturbations to it, but it's a very simple thing of generating data sets with increasing number of holes, et cetera, et cetera. And once we've got these data sets, and we're going to generate a lot of these data sets. Yeah, so the class, apologize. So the class, red class is a positive class, blue class is a negative class.
And sort of like two-dimensional.
Yeah. And the reason why we're going to do two-dimensional data set is because it's going to directly let us compute the homology of the decision boundary of a neural network, exactly compute it. So as opposed to sort of persistent homological approaches where you're kind of approximating the homology of the decision boundary, we can look at exactly what the homology is here. And by essentially plastering a grid on this 2D space, and you'll see in a moment how this works out. Yeah?
As for example, as the last picture, so how do you deal with the scattered blue points? You will think that all the points other than the red points are blue, or in fact they are kind of...
Everything is blue. Everything is blue here. So I've kind of added some alpha here because there's a concentration around the red circle. And this is just essentially to help the optimization here. So I'm not necessarily capturing which ones, like let's say we have a natural data set, right, with a certain distribution. You often won't find a huge concentration around like one class, right? It'll be sort of dispersed. Hopefully if you take a random sampling of the distribution, it'll be sort of dispersed. But this is merely just to help the optimization. So we start out with about...
So how about this very empty place? Do you think it's blue or it's red in your...
This? I mean, we'll suppose it's blue, but it's really...
Why do you think it's blue?
I've decided, this is like synthetic data sets. We're designing the distribution to be this way. So sure, there's not enough points sampled in this picture, but if you take like 100,000 points in this data set, this will be filled with blue points. We've designed the distribution. So we start with the distribution, then sample from it. And the only reason we're doing this is we're trying to say, okay, guide stochastic gradient descent with a bunch of different neural networks to at least express these regions nicely. And this isn't an exact characterization we're about to give here, but what it will do is kind of upper bound the characterization in a nice way. So we're going to generate a bunch of synthetic data sets, okay, with different homological complexities. And just at first glance, we're going to compute the persistent homology of the data. So this is sort of the notion of, can you actually compute the homology of different data sets, which just basically look like many points. So if you zoomed in on this data set, right, you got close enough, well, you find that, there's a bunch of different connected components here, right? Like each point is its own separated connected component, right? And so there really isn't any interesting topology here. But persistent homology gives you this tool sort of from an aesthetical perspective to recover the homology of the original space. So there's this nice work, and I'll kind of explain the algorithm. You may have heard about this before, but essentially you take all the points in a sort of a class of your data set and you grow balls around these points. And as these balls start to intersect, you form sort of a graph structure. And as in higher dimension, you form sort of the simplicial structure on the space. And at every single size of these balls, we'll call it epsilon, you sort of compute the number of connected components. So in this example, as we grow epsilon more and more, right, these balls are completely disjoint, so there should be as many connected components as there are balls in the data set. And eventually there's a threshold point where some of them start to merge, right? And if we keep going here, as epsilon increases, somehow some of them start forming these holes. So here's an example of a hole. At epsilon equals 7, a hole starts to emerge here, right? There's this one little pixel on which these data sets are sort of forming a hole. And if you keep increasing this, you get this sort of persistence diagram which says, when does a connected component emerge, and when does it die? When does it merge with another connected component? And the same thing for these holes. So the one valid question you might ask is, why is this even the right way to sort of compute the homology of the space? And there's two sort of points here. One is from a statistical perspective. You can use various methods. There's actually a whole body of literature which describes bootstrapping methods, which gives confidence bands on the topology of your space. So you start with some distribution, you sample a bunch of points, and if you compute the persistent homology on certain subsets of those points, randomized subsets of those points, you can build a confidence band on how probable is it that the data really expresses these sort of, or the distribution really expresses this homology. The other thing here is, for the purposes of architecture selection, we're actually going to not need an exact characterization of the space. We could even have a pessimistic characterization of the space. So for example, let's say there's only really one hole in our space, and for some reason, like as I grew balls around this thing, there was a hole that emerged here, right? That's not a real hole in the distribution, but you can sort of have a computational budget here. So for architecture selection, I have 700 GPUs or I have 100 GPUs. The same thing holds here. If I'm willing to be a little bit more pessimistic about my data set and I have more computational resources, as I grow these balls around these certain points, I could say, well, there may not be a hole here, but if there is, I would be damned to choose an architecture that doesn't express it. So for the purposes of architecture selection, persistent homology is actually sort of okay as an algorithm. So just as a sanity check for this empirical characterization, does real data have sort of non-trivial homology to it? So just to give you an example here, we take a UCI data set. This is an 8-dimensional data set. Right here is a 2-dimensional embedding of that data set just for visualization, but we compute the homology on the data set in 8 dimensions. And if you do this, you can actually see that there's these non-trivial sort of connected components emerging in the data set and non-trivial holes. And a really good example here is if you look at the cars class on CFAR, you provide sort of a lossless embedding of this cars class into sort of 9-dimensional space. Lossless is kind of a rough term here, but you actually can sort of see that if you looked at the sort of persistence diagram for this thing, there's rings that emerge. And the intuition behind this is that if you look at the cars sort of class, there's different orientations of the car, right? And so you should expect that there's sort of a one-parameter family of these cars that forms a circle, a 1D circle. So this is just sort of the first inkling here. Does anyone have questions at this point? This is just a sort of sanity check, and I want to make sure we're all on the same page.
Maybe this is sort of an aside, but how did you embed the cars into a 9-dimensional space?
Right. So I mean, I've tried a few others. There's a few papers on this. I tried TSNE and a few LLE and isometric embedding, and I chose the one which had the least loss and that was known to preserve homology. So there's an empirical characterization I can point you to afterwards that says, for these certain embeddings, they're better preserving the persistent homology of the original space. So I'm just trying to give a high-level characterization here. So we've got a way to compute the homology of the data. We've generated synthetic data sets. And now we want to say which neural networks can actually express these data sets. So all we'll do is we'll train neural networks of increasing architectural complexity on these data sets, 5, 7, 9, et cetera. And we're going to train a very large number of these neural networks on these data sets, including in depth for the neural networks. And what you get is you get a few phenomena. So the first thing that pops out is these things called topological phase transitions here. So I'm plotting the minimum error or the best performing error for a single hidden layer. Yeah, what's up?
Non-linearities matter at all?
Non-linearities do matter.
Right.
So in this characterization, I'm doing ReLU right now, just for the empirical point. But I can give you sort of theoretical intuition why they do matter. And in fact, ReLU is more expressive than hard thresholding, et cetera. But so just sort of the key is clear here. Blue is 1 hidden unit on the first layer. Green is 2 hidden units. 3 is et cetera, et cetera. So these are the colors, and you can kind of see it evident in the last picture. But let me walk you through this. So if you generate data sets that have sort of 2 connected components and nothing else, and you look at the best performing neural network with 1 layer, 1 hidden unit, 2 hidden unit, 3 hidden unit, 4 hidden unit, 5, 6, 7, 8, and so on and so forth, as you increase the number of hidden units, there's these sort of bands where the neural networks never converge, like in the best performing case. And there's these points that you'll see in the next picture, which basically are these moments at which the neural network can express the homology. And they kind of very nicely correspond with how this error convergence works. So if you look at 1 layer versus 2 layers, or even more complex homological components, you can see, well, in the case of 2 connected components for the data set, these 3 neural networks with 1 layer can express the homology. But if we go to 3 connected components, well, now it's not only 3, but it's 4 neural networks that can express the homology. So we're basically going to build up this empirical characterization, and we're going to try this out on increasing number of homological complexity and increasing number of neurons. And if you sort of, yeah.
There's something that's going against conventional wisdom, right? I would have expected from an appeal to model capacity arguments that once I hit enough hidden units that the thing becomes representable.
Yes.
The adding more capacity should slow down my generalizing. I don't know. So are you reporting like the test error, or are you reporting training?
Training. And I'm sampling a lot of points here. So the main thing is I really just want to focus on if it's going to express the homology.
Right. So the thing. I mean, I understand that if a 4 hidden unit thing can express it, so will a 7 hidden unit thing.
Yeah.
I don't see why consistently the 7 hidden unit thing must train to represent that faster than the 4.
So the speed here, I haven't even characterized. And
Okay.
So I'll actually give you a slide here in a second, and it talks about the speed, right? So if I were to, basically say, okay, if I have a certain homology in my data set, so 2 connected components, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and if I were to look at with 1 layer, sort of how long it takes for the neural network to express the homology, you get these nice bands that emerge. But I can't really say anything more about that. I mean, so basically, with 2 connected components, the neural network with 4 hidden units takes 100 times whatever number of iterations, and then so on, it sort of decreases monotonically here, and then it kind of stabilizes. But you'll notice, here, I don't have a statistically significant enough sample, right? There's more work needs to be done in this area, but you can sort of see these nice bands emerging. But I'll come back to that in a moment. I just want to kind of express what I think is the most important thing here, which is in this homological characterization. So if you looked at the data homology, and you just, first of all, look at the number of connected components, and you took 1 layer neural networks, and you said, what is the probability that at some point during training, the neural network expressed the homology of the data set, okay? And you sort of plotted this sort of against the number of hidden units. So this is the number of hidden units minus 2. I apologize, the plot axis didn't work out here. But if you look at a homology of 3 and sort of the 5 hidden units or something like this, you start seeing the probability sort of increase in this nice way. And if you look at sort of for 1 layer neural networks, you can kind of build up this nice linear relationship. For 2 layer neural networks, if you sort of go off this graph, it starts curving down in a very nice way. For 3 layer neural networks, you can see it's much easier to express the homology. And for 4 layer neural networks, it is almost trivial to express these very early connected components.
Every layer has x-axis number.
So I'm just looking at the first, just the architectures here. The first layer has these number of hidden units, and after that, it's basically the dimension of the data set, so that I can sort of preserve by homeomorphism if the thing is full rank.
So by First, by one layer, you mean you have only one hidden layer.
Yeah, so
this from 5 units, then you can, with some probability, you can express you can reduce the training error to 0.
No, you can express the homology. So you can express the number of components, not necessarily. So for example, this data set right here, this is like squiggly data set, right? So here's my data set. I'm going to cut out this ring in the middle. Okay, so this this is one connected component, and you can't expect a 5 hidden unit neural network to express, this class. This is very, very complicated. This is the curvature argument that he brought up earlier. But what this is saying is that the homology is at least expressed. So
what your experiments measure is the training error. So how do you?
They measure homology. So every single time I record this training error, this is a lot of data. So I get up here to a petabyte. But so every time you record one of these ticks, I take the entire decision, or the entire output of the neural network, and then I compute the homology of the sublevel sets. And then I take the sublevel set, which is greater than 0, and it tells me exactly what the homology is. So if I go back to this picture over here, I literally take a grid. And this grid is like 600 by 600, but I'll be a little bit more coarse here. I'll take a grid of 200 by 200 and get the exact values. And there's a way that I can sort of compute the number of holes for values which are greater than 0 in this decision boundary. And I do that for every single tick. And that's what lets me come up with this sort of nice probabilistic statement, not just about the error, but about the homology, because that's what we really care about. Like for me to say that I'm going to characterize under which conditions the error converges to 0, and I'm a little dubious about that claim. But what I'm not dubious about is sort of characterizing the homology.
So with how many units you can reduce the training error to 0?
Well, I mean I wish I could answer that question. And I can tell you something like this, right? So this next thing basically says, if I have a certain homology, then mind you, this isn't a statement about all homologies. It's about data sets which have homologies generated by this very particular way. Like I have this picture here, which says the data sets look like this, right? But I could stretch this data set this way and sort of perturb it and apply a random sort of continuous mapping to it that would change this picture.
Why I ask this question is because we know that for one hidden neural networks, we can kind of get the global minimum by training. So as long as you reach the number of hidden units that is required to reduce the training error to 0, then I think you can represent the homology. Then
yeah, of course.
Suppose that the curve should not be going like this, but it will be going like this and then going like this, and then suddenly it will all yellow on the left side. So
okay, so
there's a phase transition there maybe.
Yeah, the phase transition for homology is like this, right? Like this point, right? Roughly these points are going to express the homology, right? Like everything above this point is really expressing the homology. If I looked at the black regions, you could kind of see.
I expect the one hidden layer picture more like the 4 hidden layer picture.
Well, why do you expect? So this is in terms of the number of hidden units, right?
Yeah.
And this is in terms of the homology, right? So as I increase the homology, you'd expect it actually takes I need more hidden units. So this is a result that's really classical in sort of the neural network literature, which is like if I have a certain number of connected regions, I need. You see what I'm saying? So the picture is really as I increase data complexity, where do these phase transitions happen? That's the better way to phrase this. Okay, so you get these nice characterizations. So well, if we go to one-dimensional holes, right? So for one layer, it's really difficult to express these, probabilistically speaking, these one-dimensional holes.
So what's the probability over? How do you define probability over? Just sampling random.
I'm sampling these random data sets that I've generated, and in this case, I'm aggregating regardless of the number of connected components. I'm saying, if I have the 100 connected components and I have one hole that will express it, et cetera, et cetera, et cetera, roughly I'm kind of contracting the number of connected components and making that a very small space. But the idea is that with these 4 hidden layer neural networks, you can express these holes a lot more readily. And there's a nice relationship here.
How confident are you that your data generation mechanism is representative
of the homology?
Yeah, because you're saying probably expressing H1 with D.
Well, so
caveat, we're generating data this way, right? So this is a very conclusive kind of claim.
Well, okay, so right. So we're generating data in this particular way. Well, So I guess one thing is that it could be nicer than this. So like the curve could be over here, right? So the data could be even harder to learn on, and so that it's sort of not nice enough so that these neural networks will converge to sort of express the homology. I'm not talking about error, but the data may be even harder for the stochastic gradient descent algorithm to have these homologies pop up. But at least this is sort of giving you a nicer upper bound, right? Like at least I'm giving you sort of an upper bound on what this lower bound is. So,
for example, possibly if you have like for circles, instead of having a circle, maybe have a disk will actually
or a triangle, right? Yeah.
Disk because not a disk, a square, because neural network favors the coordinate basis, the standard coordinate basis.
Right. So, yeah. So conceivably the bounds could be lower here. This is just at a high level to illustrate that like there is sort of this increasing relationship happening here, and since I'm restricting sort of the geometry of each data set to be the same, so these are circles every single time, right? The fact that this sort of curvature changes as the number of layers expresses, it could be confounded by the fact that curvature is easier to express with more layers, right? Like but at least this is providing an upper bound, right? Like
a priori, I feel like this is kind of what you expect. So what would you say is the unexpected insight you gain after doing the experiment?
Well, okay, yeah. So the unexpected insight is that this relationship between connected components is sort of polynomial, if that makes any sense. And the additional insight here is this sort of characterization of the number of holes. So that's essentially what we get, because if you look at the other results in sort of characterizing the topology of neural nets, it's on the sum of the Betty numbers. So the Bianchini work just says, well, sum of the Betty numbers must be exponential, but not actually giving you an exact sort of characterization here. And so this is saying that, well, these one-dimensional holes matter, but they really matter in terms of depth, not the number of hidden units. And the same sort of, well, they do sort of matter in the number of hidden units, but depth plays a much more crucial role here than you would expect. I mean, if you looked at Bianchini bounds, you'd have no idea whether or not depth relates to the number of 1D holes, 2D holes, 0D holes. This sort of opens insight that these different homological degrees matter.
Also, the data set is two-dimensional?
Yeah.
They're all two-dimensional?
Yeah.
So how would you expect this to change if you go to like dimension of M?
Well, I can give you sort of a theoretical perspective, at least on the number of connected components, right? Like to express connected component, I need, yeah.
Okay, but for H1, for example.
For H1, for example?
Yeah.
I don't have any idea how that's going to change. But the intuition that is that, if you kind of are expressing a cavity, for example, if you look at the highest homological degree, right? You can use the same sort of argument. The question is what's more interesting is sort of what happens in between. So the highest homological degree, to express sort of a cavity, right? You can imagine this polytope with an empty center. You still, like, if you increase the number of dimensions, you have to increase the number of units to do that. In the same way that you express the number of sort of zero-dimensional homology connected components. But what happens in between, that's a very interesting sort of characterization. The trouble with doing this thing sort of empirically is that, if you want to go to higher dimensions, I told you that I literally made a grid and then computed the sublevel set. So your data complexity increases exponentially. And so, I mean, this is already a very, very intensive experiment to run out.
Right.
But at least provide some insight that, hey, these intermediate homological degrees sort of matter. Or higher, it's not just connected components. Yeah.
So one thing I think Peng-Chuan and I both were going down the same rabbit hole was we were confused by probability. I think it might have been better to call it like fraction of times.
Yeah, frequentist, fraction. Yeah, sorry.
Because the rabbit hole I went down was maybe the right measure to think about these probabilities is where you were like randomly sampling neural network weights for each of these things and then computing the
Sure, yeah. So
it's not quite that.
Yeah, so it's frequency of times. I mean,
yeah, so like a fraction of times this.
Right, because I'm sort of conditioning on right.
Because
I mean, I do sample like all of these different, like for each of these squares, it's like
right, but it's like trained on a sample data distribution, so it's not clear what's the right probability measure that.
Sure, right, yeah. So like I have to go over all data distributions with a certain homology, and that's not. Yeah, so it's for these points. I mean, at least I'm still sampling over all of like a very large numbers of weights in this space. it's same thing for the, I guess, like the different data sets. I have a very large number of different data sets with the same homology that I'm expressing. But yeah, there's some interesting caveats here. Just like from an experimental perspective, almost impossible. What this is telling you is that these homological degrees that are higher than 0 do matter, and their relationship isn't just in the number of units, it's also in the number of layers. And this plays out in the ReLU case too, or specifically rather in the ReLU case. Okay, so you can come up with this empirical characterization. You can also talk about, at least for these data sets, how long does it take for these neural networks to sort of converge to like 0.05 error, 0.001 error, et cetera. And you kind of get these nice bands that emerge here, as you expect. So if you increase the homology, overall the time to converge sort of increases in this fashion right here. I don't have any conjectures on what the relationship is exactly, but there is sort of this increasing relationship. And it kind of breaks down as you increase the number of layers. And I suspect that's a statistical insignificance sort of piece, but that's an open question. So basically I made this conjecture that this thing, if you extended this diagram all the way out off of this page, it sort of looks like this polynomial relationship. In particular, if you extend it off, you get for 4 layers, it sort of looks like the 4th root of the number of connected components. And for the 3 layers, you get that it looks like the 3rd root, et cetera, et cetera. And so I make this conjecture, which would be interesting to prove, that the phase transition point, the point at which it expresses the homology, is going to be somehow greater than or equal to, lower bounded by this Lth root of the Betti number. And if you do multilinear regression on all of the sort of frequencies with which this thing converges, and you basically get that it's the first Betti number times this Lth root that you get here. This is roughly what pops out. And if you sort of take a bunch of data sets,
there's something that's like tripping me up right now. If I take a homological space and flip the labels of all the classes, so if I look at the complement of something, it feels like I have a different homological characterization, right? If you think about rings.
Right, so I'm characterizing the decision regions, right? Like, I'm not literally going to the decision boundary. So, like, that's right. So, for example, and this is something that comes up. This would be a great next step in the empirical side. Is like, yeah, I know exactly what you're saying. So, like, let's say this goes off to infinity, this ball, and, on one hand, this is the number of red components, it's 1, right? So I'm saying 1 versus all, right? This is one connected component. But if I take the other notion, if 1 versus all in the opposite class, it's 1, 1, right? So the characterization is different.
Yeah.
But there's this nice sort of machinery that was developed, I think, in 2015, which says, the right way to actually look at sort of characterizing the capacity of neural nets is or not neural nets, but any given classifier is in the actual decision boundary. What isn't sort of clear is are there the nice statistical guarantees that I was talking about earlier. So what it does essentially is you've got one class over here, right? This dot class and this sort of minus class inside. Sorry, these minuses look like dots. And what you do is you sort of connect sort of as epsilon grows the minus class to the dot class. Okay, and you sort of connect as epsilon grows wider and wider. And if there's sort of a mutual connection, you make a triangle out of it. And if there's another mutual connection, you make a triangle out of it, and so on and so forth. And what isn't invariant to flipping the class is if you sort of get the simplex out of this, it's something that looks like this, right? Like, I'm being a little rough here, but you'll get a bunch of triangles which have an empty point in the middle. And it doesn't matter how you flip the classes here, this thing still has a homology of sort of one, there's like one connected component and one central hole in it. So there's a way to compute the homology of a decision boundary. And so we're just talking about we're really computing the homology of like the region, the decision region for one class. But if you sort of give the nice statistical guarantees for this algorithm, then I think approaching this work from that perspective is the right way, at least for classification problems.
There's actually a very easy answer to your question.
Okay.
If you don't look at the Euclidean space, but you look at the compactification, so you get the Euclidean space inside a sphere. So like the reverse is stereotypical stereo or whatever.
Projection.
Yeah. So that projects from sphere into plane, right? We go to reverse, right? So if you do that, then there's an isomorphism for nice spaces, like an X inside a sphere, and its complement in terms of homology. So like side statement is that if X is a certain nice subset of the sphere, and Y is a complement of that, then there is like a isomorphism between homology of X and cohomology of Y in the appropriate sense. So there is an like duality there. It's called Alexander duality. But you cannot look at it over the plane. For example, in that example, if the ball stretches to infinity, like think of the point at infinity, like there's a point in infinity that kind of wraps everything around. So if you reverse a stereotypical projection, whatever projection, right? If that is a ball, like the outside region is also a disk. Like if you have a sphere, and then like the disk inside is like the lower hemisphere, then the surrounding region is the upper hemisphere. They have the same essentially homology.
Yeah.
So there is a duality there. So when you flip it, when you compactify to the sphere, you do have this kind of duality.
From a practical perspective, though, you want to do a decision boundary, right? Like, because that's the difficulty of your learning problem. It doesn't matter if your class 1 has 500 holes, class 2 has 300 holes. If it's a linear separation, it's a linear separation. So, but yeah, that's a nice theoretical perspective. Thanks for bringing that up. I totally forgot about that.
Let's move a little faster.
Yeah, go. Okay, so you can sort of take random data sets and come up with a confidence interval on how many holes they have, and then throw in this sort of model and kind of predict sort of a phase transition point. The caveat here is it's still a lower bound, right? So there's might be data sets with higher curvature. So like these two data sets, for example. I do the persistent homology, sort of take the connected components which fall outside of like a 2 sigma sort of confidence band, and then predict the number of hidden units based on the regression I did on the empirical data. But it's still a lower bound. So you sort of can get predictions which are far below it. But the idea here is if you sort of take this as an archetype for sort of seeding architectural selection, it will be a lot nicer to restrict some subset of the space. So if I gave a higher dimensional homological characterization, so B1, B2, B3, B4, somehow understood how neural networks behaved in that case, you'd expect the fidelity of this prediction to improve. And at least as a seed for Bayesian optimization or a seed for neural architecture search, using homological features might be a plausible way forward here. But this is all empirical characterization, and there are caveats here that we talked about. But one interesting thing would be to actually somehow understand what is the exact relationship. So in understanding the exact relationship between the decision region of a neural network and sort of its homology, there's some work that basically sums the Betty numbers. It sums the number of holes in all the dimensions, and you can kind of get different relationships or different activation functions. But there's a question is, can you get an exact relationship? So to do the method we said here was, you need to get the persistent homology of the data, and that'll tell you sort of the Betty numbers in each dimension, and maybe the sum of Betty numbers is sort of a weaker characterization. So how do we compute the homology of a neural network? So we start with the data set M, and we basically want to answer this neural architectural selection question, right? So which architectures are such that there is some F in the architecture class that expresses the homology. So neural homology theory is kind of broken down like this. You start with some sort of neural network here, and you convert it to a set algebraic expression. And for neural networks with ReLU and half-space functions, you can sort of do this. There's actually a very nice way of doing this. So you convert this neural network and its weights to some set algebraic expression, A union B union C, or A union intersect, or A union B intersect C, or A union B intersect the complement of C, etc. And then you can apply this sort of nice tooling in the Meyer-Viator sequence, and I'll just really kind of make this high school algebra for you, but to actually kind of count the number of regions in your space. So I'm going to break down each of these sort of components. Okay, so the first thing you start with is, well, the decision region of a single hidden unit is a half space if you're using ReLU or ReLU-like functions, like the hard thresholding functions. That's the first given. I hope this is sort of clear to everyone. The next thing is, if you sort of go deeper in a neural network, you've got all these half spaces for like a single layer, multi-layer, or single layer perceptron. But if you go deeper in the neural network, what's happening? We're going to restrict ourselves to hard thresholding functions for now, but you can do the same analysis for ReLU-like functions. So just to give you a picture here, so we've got a neuron A and neuron B, and this is sort of the half space that A produces on the input space, the half space that B produces on the input space. And we've got a neuron C, which is up here, and it's acting on this sort of next layer's output space. And all you have to do really is sort of look at this. In a hard thresholding case, you're going to output 0, 1, or 0, 1, or 0, 1. So this is a binarization. And if you sort of look at the angle of this half space, it'll give you a set expression. So what this thing is saying is because C is this plane, it's saying the neural network is only going to be active if we have the first neuron HA and the second neuron HB are such that when A is active, B is not active. When A is active, B is active. Or if B is active, A is not active. So if I actually were to write this out, right, you just compute the set algebra and you get A union B. So that's the decision region of this neural network. And there's these nice tools in homology that will let you look at sort of set expressions of various half spaces. Okay, so there's like a formal way to describe this. I won't get into it now, but there's some machinery we can talk about afterwards. But how do we sort of compute the number of holes given a set expression of half spaces? So I'm going to set up some notation first really quickly. And I'm going to show you kind of looks like kind of high school algebra when you work out the math here. So I'm going to write A plus B as A union B, A intersects B as A times B. And then if I want to sum the number of holes, or apply this sort of summation operation. So if A has 5 holes, B has 6 holes, I want to sum them, I'm just going to write A circle plus B. And if I want to subtract the number of holes, I'm going to write A divided by B. And I'm going to drop the H for this talk. So this expression, just notationally, right, like A O plus B divided by A B plus C O plus D is just actually equal to this thing notationally. Everybody good on this notation? So H is just the number of holes. We can just think about like that.
So like the plus goes has operator precedence over the circle plus?
Well, so I haven't said how these things sort of distribute yet.
Yeah, because for that correspondence to work in the bottom, you have to have the plus go before the O plus.
No, but otherwise the thing does not even type check, right?
Yeah.
Yeah. I mean, I'm being kind of lousy here with this notation, but just to kind of give a high-level picture of what's happening here. But like I would put some parentheses. I would put the parentheses around this first.
That's fine.
Yeah.
No other interpretation type checks, so this has to be the right interpretation.
Okay. Okay, so now I'm going to really kind of graze over how this works in homology. So let's say we've got these set expressions, A, B plus C, and we want to compute the homology of them. I'm going to pretend like we're in the 1D case right now because it works out pretty nicely. So we're just going to look at the number of connected components. So we know for any half space, the homology of that half space in 1D is 1. Like the number of connected components is 1. And we've got this rule. So we can sort of kind of extract, if we have A, O plus B, then it's equal to A, B, O plus A plus B. This is just a nice little rule. I'm going to take it as given. If you know homology, this is Meyer-Vietoris on cotorsion or torsion-free homology without higher dimensional homology, but I'm just going to say this is a rule. And then an initial rule here, which is also going to require some restrictions on how we're computing homology. It says if C is equal to A, O plus B, then A is equal to C divided by B. This is just nice little algebraic rules here. And then normal set operation works. So A times B plus C is equal to AB plus AC. And then AABC is equal to ABC. So we've got this sort of high school level algebra here with some rules. And if we have a set expression, we're going to write it as what it is, AB plus C. We're going to apply this rule number 1. So basically on the left side, we've got, AB is equal to A in this rule 1. And on the right side, C is equal to B. And so we're going to apply rule 1 and 2 here and sort of keep applying these rules. And you just imagine working on this like normal algebra. I'm going to skip over how these rules work out in this case. But you can say that the number of holes is equal to 3 because A plus B plus C is 3 minus sort of whatever the homology of A intersect B intersect C is plus the homology of A union B. And this is already nice because you can kind of get a nice upper bound on the number of connected components just by this really simple algebraic expression. So just like as a simple question here, can a 3 hidden unit neural network be generated in a data set with H0 of m equal to 10? Homology theory says no. So the proof looks like the following. So you start with this neural network like this. You somehow convert this neural network and its weights to a set expression. In this case, the weights are such that you get A union B union C for these half spaces. Then you apply this set algebra. I'm just going to go through it really quickly. And if you work through the derivation, you can sort of use these very simple algebraic rules to define sort of upper bound. So like one really nice upper bound you can come up with is with the 0th dimensional homology, or the number of connected components of a neural network with these heavy side step functions as activation functions, is bounded by n. And if you go, you increase the number of layers, it's bounded by n to the L. So that's just a nice result that sort of pops out here. But this is very preliminary work, and we haven't really developed a lot of this theory, but it's sort of the inkling of how you might go about proving these homological questions. So that's all I have for now. You can check out the paper on arXiv, and if you have any questions, I'm happy to answer them.
So your algebra is only for H0?
Well, so I mean, I'm sort of omitting, like you're going to have to compute the current, like we can sit down and talk about this afterwards, but like you have to sort of compute the kernel, and you can work up the Meyer-Vier-Torre sequence and do something nice here. But in this example, I'm just being very simple because I wanted to sort of explain this to people who haven't seen homology before.
It seems pretty impactful for just large, either dimension or a large number of neurons.
Yeah. Right. Yeah, so one question I have in this case is sort of, in hyperplane arrangement theory, right, you can sort of compute the homology, and it's kind of subject to how fast you can compute the intersection lattice. Do certain sparsity conditions in neural networks make the intersection lattice of half spaces easier to sort of compute? Is computing intersection of half spaces easier or harder than the intersection of hyperplane arrangements? So on and so forth. Those questions are going to tell you how intractable this is. Starting this way and sort of, trying to, if you were to build an algorithm that computed the homology of a neural network by literally manipulating these set algebraic expressions, you get exponentially many terms if you go deep and you do it naively. So this isn't the way you write the algorithm. But this is conceivably a way you can prove things in a sort of nicer format. So that's sort of where this is going. For proofs, this is a nice mechanism. I think for an algorithm, it's very naive.
So I want to ask one question. Do you expect an efficient algorithm to solve this problem? So I will give you a neural network architecture, and also I will give you the Betti numbers for this d-dimensional data set. And can you have an efficient algorithm to see whether this neural network can represent this topology?
Yeah, so that's an open question, I hope.
What's the difficulty?
The difficulty is going to be in so the main mechanism thing here that I'm kind of imagining is that you have to take, first of all, you have to take these half spaces, and you have to somehow compute their intersections, right? So like with the first layer, it's pretty easy to do this, but you still get a lot of terms. So you have to compute the intersection of half spaces, and then somehow this will give you the homology of your space, the number of holes. And as you add more layers, this is going to depend on the following thing: does the intersection of half space problem, as you go deeper, blow up exponentially, or can you sort of use in a nice way that all the work you've already done on the first layer? So I could keep enumerating conditions here that make me think that this isn't intractable right off the bat, but it's an open question. The ideal dream is if you could compute the homology of a neural network from its data, there's tons of things you could do. You could do away with persistence homology, right? You could come up with a sort of parametric version of homology computation. You train a neural network, compute the homology of its decision boundary, and say, well, the data set has to at least contain these things with the confidence that you have in your classifier. Another thing you could do is say two neural networks are performing really, really well on ImageNet, and they get the same testing error. But one has like 500 connected components in its decision boundary. Those are all adversarial pockets, right? If it's getting the same testing error, how do you tell which neural network is simpler in its decision boundary?
By the way, just one comment. I suggest you not use, from my perspective, maybe the usage of adversarial samples are kind of
the word
here. In fact, what you mean is that you will get wrong labels, but not adversarial samples. Adversarial samples is related to the margin of your decision boundary. Whether, okay, now you
got it.
right,
okay. So that's the definition
you jump
of
a
adversarial.
little bit, whether you will jump into another one. If you have a large margin, you do not have adversarial samples. But in your setting, you are talking about, I think, classification.
So there'll be pockets of classification error that you wouldn't anticipate. One thing, though, if you really are to use this definition of adversarial examples, is because you're using these linear half spaces instead of like a different shape, for example, right? That's going to give you a certain increase in homology. Where do these extra homological components live? Are they really far away from your margin, or are they like right on the margin? That's another thing, right? It could be very well that happens, but thank you for the correction. Yeah, so there will be like one way to choose an architecture would be conceivably they're both doing well in testing error, but one has way less of these sort of homological complexities. And homological complexities are room for sort of misclassification. So choose the one that's simpler. Yeah.
It's a basic question, right? So, are there analogs of these homological complexities, but for manifolds? The reason I ask is because the kinds of models you're studying, these neural networks do have like local Euclidean smoothness, right? They do have a smooth inductive bias, at least locally. So manifold seems to be the
really, or like hard nonlinearities. But okay, so assume have a smooth one.
smooth ones, right?
Sure.
So it seems like why not understand like the more specialized thing and like rely on manifold theory rather than try to stay more general at topological theory, right? And then like the sort of additive to that is like the neural homological theory is cool, but it seems like it's more broadly applicable. After doing all this work trying to do data set characterization through topological complexities, like homological complexities, like this could apply to decision trees too, right?
Yeah,
you have
that's right.
half spaces.
That's right.
Like,
That's right.
so
Maybe it's easier to even do this.
Yeah, exactly.
Yeah, it's more broad. I'm calling it neural homology theory too, because this is where it came from. This is like where the. But yeah, absolutely.
Yeah, so I'm like, if you want to go neural and you're thinking about some classes of nonlinearities, maybe the right thing to do is to like specialize things further and think about like the
manifold structure. Right. Yeah. The main reason why I'm just starting with this topological perspective is that, well, you know, in some cases, it's actually conceivable that you can compute this on the data. Obviously, in high dimensional cases, it breaks down. But it's, you know, I mean, it's not clear if I use certain manifold properties of neural nets and characterize them that way, that would even help in sort of seeding architecture selection. The main point, or the initial point of this work was justifying why homology would be something nice to feed into a neural architecture search. Right? Somehow that it really does sort of affect which neural networks you should choose. It's one piece of inductive bias you can use in choosing neural networks. And the main thing is you have to be able to compute that geometric complexity, compute that inductive bias. So from a theoretical perspective, I think making more specialized notions for neural nets is really nice, right? Because it applies to arbitrary half spaces. But from sort of computational perspective, having this computable topological measure would be really nice. So.
Yeah, I'm not convinced that like focusing on topology, like I don't feel like data complexity is a function, like, or topology doesn't really capture data complexity that well. Like if you, for example, have two clusters that are very close together, like topologically they're the same as if they're far apart, but like I think that's much more difficult to learn.
Right. Yeah. I mean, I can come up with 1,000,001 counterexamples for this.
Yeah.
Right. But there's sort of like I guess the notion was that like the topology can't be your only inductive piece of inductive bias, but I think it is one piece, and we should have at least one piece that we understand well.
Okay.
Yeah. That's another one. If you can characterize that and then come up with an algorithm for it, then let's do that characterization too.
There was one remark about the sanity check, and I thought it would be like just really cool to like demonstrate it. Often it boils down to like the rotational invariance of images too, right? And we often say that lies on a much lower dimensional manifold than like the RGB pixel space that we represent things in. It would be really cool to just actually do it and visualize it. Like just literally take the same object, take a whole.
Well, there's a great image of this. It's like a manifold embedding of like ducks, rotated ducks.
Oh, never mind. Ducks. Okay, never mind.
Oh, is it?
I thought you were going to say the Klein bottle example.
Well, but this one's way simpler because it's just like literally like you could take a bunch of ducks that are rotated, and it gives you this like nice circle when you embed it. Like there's a good picture.
No, but without appeal to embedding, right? Like start in the original data representation.
How do you visualize the circle?
No, the persistent homological thing, you should essentially see that.
Okay, yeah, that would be a nice, simple example as opposed to capturing those. Yeah,
I'm saying like don't do t-SNE, don't do any embedding. Take the original images, do this persistent homology thing, and like argue that.
That'd be a good picture.
What? Compute though.
Yeah, he seems to have petabytes. Petaflops.
I've got compute.
Ask Russ. Ask Apple.
It's public.
All right. Cool. Thanks.